Hi everyone, in this video we're going to go over page 13 and select problems on page 14 and 15. This section is called implicit differentiation. It says, suppose we wanted to find the derivative of x squared plus y squared equals 16. What would we have to do first? So in all of the previous examples we would need y by itself, so we would have to solve for y. If we solve for y in this case, we could subtract x squared on both sides. And then we could square root the y. Now, if I just type this into my calculator and this into my calculator, they're not going to look the same. This is actually only half of the graph of this. This is actually the graph of a circle. But this will only show you half of the graph of the circle. The reason why is because when we take the square root, we really need a positive and negative version of this. So to get the full circle that is graphed right here, we would need to graph two things. We would need to graph square root of 16 minus x squared and negative square root of 16 minus x squared. So this would actually turn into two functions. Y equals this and y equals negative, so positive and negative versions. Now, we're not going to differentiate randomly with two different representations of a function. So this is where we're going to use something called implicit differentiation. A lot of the functions you see in this section, they're going to kind of look crazier than this. They're not necessarily going to be very easy to solve for y. This one was easy in comparison. So this is the technique we're going to use. Implicit differentiation is an application of the chain rule. Again, you're going to see functions in implicit form like this, x times y equals 10. That one again is also really easy to solve for y, because you would just divide by x on both sides and you would end up with 10 over x. That's called the explicit form. This is what we've been using more commonly. When we do this implicit differentiation, so we're going to do the derivative of this, we're going to just differentiate normally, but anytime we see a y, we have to pretend that y is its own function. All right, and this is kind of what I'm going over in right here. So let me show you this for 1 second before I kind of move into the implicit. So here's kind of what I mean. So think of the chain rule as really what we want to think of. If I was trying to do the derivative of this, right, I would take the 6 and move it out front. I would take the 6 and move it out front. I would decrease the exponent by 1, making that a 5. And then I'd have to do what? Multiply by the derivative of the inside. The derivative of 4x plus 5 is just 4. Now, if this was written in some way that we didn't know that 4x plus 5 was right here, here's another way you could see it. Pretend like instead of 4x plus 5 raised to the 6, we had y raised to the 6. But we didn't know that y was really 4x plus 5. So the way that we could write this derivative without knowing that y was 4x plus 5, well, we could start off the same way. We could put the 6 in the front. We could put the y, decrease our exponent by 1, and then we would have to somehow indicate that we're taking the derivative of the inside. So in this case, this was the derivative of 4x plus 5. Over here, we want the derivative, so my 4x plus 5 was here. Over here, I want the derivative of y. Well, I have no way to indicate what the derivative of y is because I don't know what function y is. If I knew that it was 4x plus 5, I would just put a 4 here. You know, whenever this changes, we would just adjust this accordingly. So when we don't know what it is, when it's in implicit form, what we're just going to indicate this with is a dy dx. So just our function for derivative. So anytime you see in these implicit functions, anytime that you see a y in there, when you do the derivative of it, you're going to have to add this extra like times dy dx to indicate that you would have done the chain rule had you known what y was. Okay, this is what this is saying in words. So for each term without a y, we're just going to differentiate normally. So if this was just x to the 6th, we would be fine. For any term with a y, like y to the 6th, we're going to differentiate normally, 6y to the 5th, but we would also indicate that we would differentiate again had we known what y was. So this is all coming back again to the chain rule. And this part right here is the big part that I was trying to go over on my little half sheet of paper over here. So if I don't know what the function is, y to the 6th, I can differentiate normally, but next to it, I'm going to put a dy dx to indicate that I would have done the chain rule had I known what y was. This only matters for the variable y. It doesn't matter for any of the other variables you'll see, aka x. It doesn't matter for x. The reason why is because we're always, it's called differentiating with respect to x. So every time we differentiate, we're assuming that x is our variable. So here, when we differentiate, x isn't our variable, so we have to indicate that we would do this extra step had we known what this was in terms of x. All right. Our goal, you might have more than one dy dx in your problem, depending on how many y's are in your question. Now, our first example didn't have very many y's, it just had that one, so that's fine. But if it has more than one y in it, you may have to do some factoring to solve. So, evaluate d dx, that just means take the derivative of x squared plus y squared equals 16. So, if I took the derivative of x squared, I would get 2x. Now here is one that's in implicit form. So if I take the derivative of y squared, that would be 2y. But then I would do the derivative of y if I knew what it was. So if it was written in terms of x. So anytime that I do a derivative that has y in it, I'm going to add this extra, I would do the chain rule if I could, step. Then I've got my equal sign, and on the other side I just have 16. The derivative of 16 is just 0. Now the goal is to get dy dx by itself, so we want to solve for the derivative. So what I'm going to do is first I'll move the 2x to the other side. And you could do some of these steps in your head, but I have 2y dy dx. Move that over to the other side. Will give me negative 2x. Now these two things, the 2y and the dy dx, are being multiplied together, so I'll have to divide to move it over to the other side. So I've got negative 2x over. So when I divide by 2y on both sides, I could actually simplify this, and I would get dy dx equals, those would cancel, negative x over y. This is my final answer. Now you can do implicit differentiation with any types of functions that are written implicitly, so like with y's in them. We're going to look at some random examples on the next couple of pages. So the first one is number 1. It says find dy dx given 2y equals x squared plus sine y. Here's an example of an equation that would be really hard to solve for y, because y is the argument of this sine function, and there's this 2y over here. All right. So we'll take the derivative of 2y. So the derivative of 2y is just 2. But because it was a function that had a y in it, we would indicate that we would have done the derivative of it if we could. So we'll do 2 and then dy dx. Then equals x squared. So we'll do the derivative of x squared, which is 2x. I don't need anything next to that because this term is in terms of x. And then plus the derivative of sine of y is cosine of y. This one has a y in it. I would have done the derivative of y if I could, so I'm going to put a dy dx next to this one. Now this example is different from the one on the previous page because there's multiple locations where there's a dy dx. So our goal is to solve for dy dx. So to do this, step 1 is to get all the dy dx on one side. And I'll write some steps up here as we go through. Okay, so let's say I move the cosine over to the other side. So I'll have 2 dy dx. Then moving that over gives me minus cosine y dy dx equals 2x. Now, I have this dy dx in both. Since they have something in common, I can use that as a greatest common factor. So I'm going to factor out a dy dx. I'll put that over here. So if I take out a dy dx, then I'll have just 2 minus cosine y. The right side is still just 2x. So the next step would be to factor out a dy dx if necessary. Not all of the questions will make you do that, like the first one, but. And now you can just finish this off. So I want to move the 2, this is being multiplied together, so I'll just have to divide it so I can move it to the other side. So dy dx equals 2x over 2 minus cosine y. So our last step is going to be just divide, divide by whatever's next to the dy dx. Okay, let's look at another one. So number 6. Look, I only have one y in this one, so I'm not going to have multiple dy dx's. X equals tan y, so the derivative of x is just 1. I don't need to write anything else because this is already in terms of x. This one is not in terms of x. The derivative of tangent of y is secant squared of y, but then I would have done the derivative of y had I known what it was in terms of x. So I'm going to write dy dx next to that one to show that I would have done the chain rule. So all of my dy dx's are on one side already. I don't need to factor it out. I can just do the dividing step. So 1 over secant squared of y is dy dx. 1 over secant squared is just cosine squared, so I could write this one like that. All right, let's check out one more that's similar. So go ahead and try x equals sine y, number 10, on the next page. So if I do the derivative of that, the derivative of x is just 1. The derivative of sine is cosine. Since this is a y, we're going to have to put a dy dx next to it. So to solve, I'll do 1 over cosine of y is dy dx. 1 over cosine is just secant, so secant of y is dy dx. Okay, let's look at these last two that I boxed right here. They're similar to each other because they have like a product built in. So sometimes you're going to have to use the product rule. So this one, the product rule is with the 18xy. And this one, the product rule is with the x and y in the middle. All right, but so we can use the 1d2 plus 2d1. So if you ever see a little product, like even this one, I'm gonna have to use the product rule when we do those. On 11, there's a product right there. 12, there's a product right there. So anytime you see something with an x and a y in it, we're going to have to use the product rule. So the left side of this equation is normal. So the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared, but again, we don't know what y is, so we'll put dy dx next to that. Now on the other side, we have the product rule. So if you want to like kind of split this up in your brain, I'm going to split the 18x, and that's going to be like function 1, and just the y will be my function 2. That's supposed to be a 1. It looks pretty terrible. Function 1. So we're going to do 1 d2 plus 2 d1. So 1 is 18x. d2, so the derivative of y is just 1 dy dx. Plus 2, function 2 is y. And the derivative of function 1, 18x, the derivative of that is 18. Oops, function 1 should be 18x. There we go. I wrote that wrong. 1 d2 plus 2 d1. There we go. Now we have everything. So we want to get all of the dy dx's on one side. So maybe we'll move everything over to the left side. This guy that doesn't have a dy dx, we want to move that over to the right side. So let's do that all at once. So we'll do 3y squared dy dx. We'll move the 18x over as well. So minus 18x dy dx. And then on the right side, we'll have this y times 18, which is just 18y. And we'll be moving this 3x squared over to the other side, minus 3x squared. So we'll have to get one of these factored out. So we'll factor out a dy dx. And that'll leave us with, oops, factor out a 3y, or a dy dx. That'll leave us with 3y squared minus 18x equals 18y minus 3x squared. So to get our final answer, we'll have to divide by 3y squared minus 18x to get this by itself. I'll put this over here, dy dx equals 18y minus 3x squared all over 3y squared minus 18x. I'm going to leave that as my final answer. You might notice that all of these could be divided by 3, so you could do something like that to simplify, but that's how I'm going to leave it. Let's try one more with product rule. Number 9. So I've got the product rule right here. So this is going to be my function 1, and this is going to be my function 2 when I get there. So I'm going to do, first I'll do the derivative of x cubed, so that's 3x squared. And then I'm going to do 1 d2, so 1 is x. d2 is the derivative of y, which is dy dx, plus 2, which is just y, and then the derivative of function 1, the derivative of x is just 1. So this whole thing is the product rule. Just like up here, this whole thing was the product rule. Now we have plus. Now I'm going to do the derivative of y cubed, so 3y squared dy dx equals the derivative of 1, which is 0. So if I simplify this a little bit, I have these dy dx's that I'm going to keep together, and this 3x squared, and this just y is really what this is. I'm going to move that to the other side. So I'm going to do this all at once. So we've got x dy dx, that's staying. 3y squared dy dx is also staying. On the right side, I'm going to move this over. So this is going to become negative 3x squared. And this is going to be moved over as well, minus y. Now I can factor out a dy dx. And I'll be left with x plus 3y squared. And then to get dy dx by itself, we'll move this to the other side by division. So dy dx equals negative 3x squared minus y all over x plus 3y squared. And that's our final answer. All right, we're going to do more of this next class. This is not the only time you're going to see this. So let me know if you have any questions. Have a good one.